Aircraft Hydraulic Systems Part 1. Part 1 will covering basic principles, types hydraulic fluids and types of pumps. Hello students, today we will learn about aircraft hydraulic system. Before proceeding to the main system, I will like to tell you about the general principle involved in aircraft hydraulic system. Hydraulics is a method of transmitting power through pipes and control devices, using liquid as the operating medium. For certain applications, hydraulic systems are used in preference to mechanical or electrical systems for a number of reasons. To mention them, they are: ease of application of force, ability to increase the applied force as necessary, ease of routing of pipelines, and elimination of backlash between components. Liquids are, for most practical purposes, incompressible, and this fact enables movement to be transmitted through pipelines, over great distances, without loss of time or motion. However, liquids will expand or contract as a result of temperature changes, and a relief valve is necessary, to prevent damage from excessive pressures, in any closed system which may be subjected to large changes of temperature. In a closed static system, pressure exerted on a liquid is transmitted equally in all directions. Figure 1 shows a simple arrangement of pistons, cylinders and pipes, which uses this principle to obtain mechanical advantage. Figure 1: Mechanical advantage by hydraulics, Pascal's law. The area of piston A is 10 mm square, and the force applied to it is 10 Newton. The pressure in the liquid is, therefore, 1 Newton per millimeter square, which is transmitted undiminished to piston B. The area of piston B is 100 mm square, and the force exerted upon it is thus 100 Newton, representing a mechanical advantage of 10:1. This advantage is obtained at the expense of distance, however, because the area of piston B is 10 times that of piston A, and piston B will move only 1/10 the distance of piston A. When liquid is in motion, its dynamic characteristics must also be taken into consideration. Friction exists between the molecules of a liquid, and between the liquid and the piping through which it flows. This friction increases with any increase in viscosity or velocity of the liquid. Friction results in some of the power available from a pump being transformed into heat, and in a reduction in pressure throughout the pipelines. Any restriction in a pipeline will increase liquid velocity and produce turbulence, resulting in reduced pressure downstream of the restriction. This fact is often exploited in system design, and a restrictor is also used to limit the rate of liquid flow, and thus the rate of movement of components such as the landing gear or flaps. We will be discussing them in detail later in this chapter. Before proceeding ahead with the description of various valves and components used in aircraft hydraulic system, we should first discuss about the hydraulic fluids. Almost any sort of liquid could be used in a hydraulic system, but the special requirements of aircraft systems have resulted in the use of vegetable, mineral and synthetic-based oils, known as hydraulic fluids, which should have the following properties. They provide good lubrication of components. Their viscosity is low enough to minimize friction in pipelines and to allow high-speed operation of motors and pumps, but high enough to prevent leakage from components. They prevent internal corrosion in the system. They have a wide operating temperature range. Hydraulic fluids are colored for recognition purpose, and fluids to different specifications must never be mixed. Fluids of the same specifications, but produced by different manufacturers, may be mixed when permitted by the appropriate maintenance manual. Use of a fluid which is not approved for a particular system may result in rapid deterioration of seals, hoses and other non-metallic parts, and may render the system inoperative. Vegetable-based fluid is normally almost colorless, and must be used with pure rubber seals and hoses. It is used in some braking systems, but is not often found in hydraulic power systems. Mineral-based fluid is normally colored red, and must be used with synthetic rubber seals and hoses. It is widely used in light aircraft braking systems, hydraulic power systems, and shock absorber struts. Synthetic-based, phosphate ester fluid is widely used on modern aircraft, mainly because of its fire resistance and extended operating temperature range. It may be colored green, purple or amber, and must only be used with butyl rubber, ethylene propylene or Teflon seals and hoses. This fluid requires extreme care in handling as it's irritant to the skin and eyes. A barrier cream should be applied to the hands and arms, and fluid-resistant gloves should be worn, whenever servicing operations on the hydraulic system are carried out. In addition, goggles should be worn whenever there is the possibility of fluid being splashed into eyes, such as when pressure testing or bleeding components. Spillage of fluid should be avoided, but, if it does occur, the area affected should immediately be wiped with a dry rag, and thoroughly washed with soap and hot water. In view of the incompatibility of different fluids, it is important that any containers, or test rigs, used for servicing aircraft, are clearly marked with the type of fluid they contain. To start with component description of various components used in aircraft hydraulic system, we will start from various types of pumps used in aircraft hydraulic system. Most modern aircraft are fitted with either fixed volume or variable volume, multi-piston type hydraulic pumps, driven from the engines. Other types of pumps, such as gear or vane positive displacement pumps, may be found in some installations, but these are generally used for powering emergency systems. Hand pumps, where fitted, are often of the double-acting type. Hand pump is an additional unit to be used in case of emergency or when the engine-driven pumps are inoperative. Power-driven pumps are the primary source of energy and may be either engine-driven, electric motor-driven, or air-driven. As a general rule, electrical motor pumps are installed for use in emergencies or during ground operations. Fixed volume pumps. Under fixed volume pump category we have axial piston pumps, gear-type pumps and vane-type pumps. Fixed volume pumps deliver a fixed quantity of fluid into the system at a particular speed of rotation, regardless of system requirements, and means must be provided for diverting pump output when it is not required in the system. These means are discussed later in lesson. One type of fixed volume multi-piston pump is illustrated in Figure 2 and it is known as axial piston pump. The cylinder block and drive shaft rotate together, and because of the angle between the cylinder block and shaft axes, each piston moves into and out of its cylinder once each revolution. The stationary valve block has two circumferential slots leading to the top of the cylinder block, which are connected to the fluid inlet and outlet ports, and are arranged so that the pistons draw fluid into the cylinders on the outward stroke, and expel fluid into the system on the inward stroke. Figure 2 axial piston pump. Now we will discuss about gear-type power pump. It's a constant displacement pump. It consists of two meshed gears that revolve in housing. It is shown in Figure 3. The driving gear is driven by the aircraft engine or some other power unit. The driven gear meshes with, and is driven by, the driving gear. Clearance between the teeth as they mesh and between the teeth and the housing is very small. The inlet port of the pump is connected to the reservoir, and the outlet port is connected to the pressure line. When the driving gear turns, as shown in Figure 3, it turns the driven gear. Fluid is captured by the teeth as they pass the inlet, and it travels around the housing and exits at the outlet. Figure 3 above and 4 below shows gear-type pump. Now I will discuss about vane-type power pump, and it is also a constant displacement pump. It consists of a housing containing 4 vanes, blades, a hollow steel rotor with slots for the vanes, and a coupling to turn the rotor shown in Figure 5. The rotor is positioned off-center within the sleeve. The vanes, which are mounted in the slots in the rotor, together with the rotor, divide the bore of the sleeve into 4 sections. As the rotor turns, each section passes one point where its volume is at a minimum and another point where its volume is at a maximum. Figure 5 shows vane-type pump. The volume gradually increases from minimum to maximum during the first half of the revolution and gradually decreases from maximum to minimum during the second half of the revolution. As the volume of a given section increases, that section is connected to the pump inlet port through a slot in the sleeve. Since a partial vacuum is produced by the increase in volume of the section, fluid is drawn into the section through the pump inlet port and the slot in the sleeve. As the rotor turns through the second half of the revolution and the volume of the given section is decreasing, fluid is displaced out of the section, through the slot in the sleeve aligned with the outlet port, and out of the pump. Variable volume pump is similar in construction to fixed volume pump. The fixed volume pump was taught before, but the cylinder block and drive shaft are coaxial and moving together. The pistons are attached to shoes which rotate against a stationary yoke, and the angle between the yoke and cylinder block is varied to increase or decrease pump stroke to suit system requirements. Figure 6 shows the operation of the pump. Figure 6 shows variable volume pump. When pressure in the system is low, as would be the case following selection of a service, spring pressure on the control piston turns the yoke to its maximum angle, and the pistons are at full stroke as pressure on the piston is minimum, delivering maximum output to the system. When the actuator has completed its stroke, pressure builds up until the control piston moves the yoke to the minimum stroke position. It does so by changing the angle of the yoke to minimum possible angle. In this position a small flow through the pump is maintained, to lubricate the working parts, overcome internal leakage and dissipate heat. On some pumps a solenoid-operated depressurizing valve is used to block delivery to the system, and to offload the pump. Next topic that I will discuss with you is hand pumps. A hand pump is included in some aircraft installations, for emergency use and for ground servicing operations. Figure below illustrates a double-acting hand pump, i.e. a pump which delivers fluid on each stroke. Figure 7 aircraft hydraulic hand pump. As we move the handle down, the piston moves upward in the cylinder. Fluid is drawn in through a non-return valve NRV at the inlet connection into the cylinder. At the same time, fluid above the piston is discharged through a non-return valve in the outlet connection. As the piston moves downwards, the inlet NRV closes and the transfer NRV opens, allowing fluid to flow through the piston, since the area below the piston is larger than the area above the piston. Part of this fluid is discharged through the outlet port. When pressure in the outlet line exceeds the relief valve setting, discharged fluid is bypassed back to the pump inlet. Before closing part 1 of aircraft hydraulic system, have a look on different videos that I have compiled for you, so as to brush up the material that I taught in this part. Thanks for watching.
Many different types of pumps exist to assist fluid movement in a variety of systems. An external gear pump uses two gears rotating against each other to provide fluid movement. One gear is driven by a motor connected to a shaft. This is called the drive gear because it is driven by a motor, and it in turn meshes with and drives the movement of the second gear. As the gears rotate away from each other and come out of mesh, they create an expanding volume on the inlet side of the pump. This creates a vacuum at the inlet port, allowing fluid to flow into the pump. Then fluid flows into the cavities and is trapped by the gear teeth. As the gears rotate, a flow path is created around the outside of each one. Fluid trapped in the slots between teeth is carried around and discharged into the cavity with the outlet port. Meshing of the teeth in the center of the pump seals the outlet port from the inlet port. No fluid passes between the gears. The advantages of external gear pumps are their high speed and pressure, relatively quiet operation, and that their design accommodates a wide variety of materials. Disadvantages include bushings in the liquid area can become worn and that they have fixed end clearances. Internal gear pumps are exceptionally versatile. This type of pump has one inner gear which is inside a second outer gear. The inner gear has a shaft driven by a motor and has teeth that protrude outward. The outer gear has teeth that protrude inward toward the center of the pump. As the inner gear rotates, it meshes with and moves the outer gear. Liquid is trapped in the gear spaces and carried from the inlet to the discharge. A stationary crescent-shaped divider separates the intake and discharge portions of the fluid. Advantages of internal gear pumps are a smooth and almost pulseless flow, and slightly more horsepower for its size. Disadvantages are its higher cost, limited size range, low to moderate pressure ratings, and few sources of manufacture. A rotary vane pump is a positive displacement pump that consists of vanes mounted to a rotor. The vanes are on an off-center drive shaft. As the shaft rotates, the variable length vanes slide in and out to maintain contact with the pump housing. The tension in the vanes is maintained by either springs or hydraulic pressure. As the vanes rotate, they create chambers of varying sizes within the pump. Fluid enters at the largest chamber. As the vanes rotate and retract, the chambers get smaller, forcing fluid to exit through the discharge port. The advantages of vane pumps are that they can handle low viscosity fluids at relatively higher pressures, can dry run for short periods, and develop a good vacuum. Their disadvantages include complexity and their unsuitability for both high pressure and high viscosity fluids. Piston pumps come in many different forms. A swash plate is a device used to translate the motion of a rotate shaft into the reciprocating motion of a piston. Swash plate piston pumps have a rotating shaft connected to a cylinder block containing pistons, which are pressed against a stationary swash plate that sits at an angle to the cylinder. As the shaft rotates, the pistons move against the swash plate, causing them to reciprocate within the piston block. The pistons create a vacuum that forces fluid in during half a revolution and expels fluid during the other half. On the intake stroke, a spring ensures the pistons pull back and maintain contact with the swash plate, causing fluid to fill the empty cavity left behind. On the discharge stroke, the angle of the swash plate forces the pistons back inside the piston block and discharges the fluid. The greater the slant on the swash plate, the further the pump pistons move and the more fluid they transfer. Piston pumps, in general, are manufactured with closer internal fits than other pumps. This means that internal slippage can be less so that they operate with reasonable efficiency at pressures both too high or too low for the operation of other pumps. Radial pumps are designed so the pistons stroke in a direction at right angles to the shaft. The pistons are arranged like wheel spokes around a cylinder block with an eccentric central cam mounted on a drive shaft. As the shaft rotates, the cam moves towards the pistons, forcing them down into the cylinder block and discharging the fluid. As the cam moves away, springs help retract the piston and cause the intake stroke. Check valves ensure that fluid only enters the inlet ports and only exits the outlet ports. Radial piston pumps have a low noise level, very high loads at low speeds, and high efficiency. Hand pumps are used when a source of power is not available or where the extra expense of a power pump isn't warranted. For example, they are used on shop presses and other portable equipment, serve as standby pumps, and serve as sources of emergency power. Hand pumps are always of piston type and are usually constructed with a piston working between two check valves. Double-acting hand pumps are more efficient, allowing fluid to both enter and discharge on both strokes of the piston. Moving the pump handle in either direction allows fluid to be drawn in from the reservoir and discharged via the outlet ports. Check valves in all locations prevent fluid backflow.
An axial piston pump is a pump that has a number of pistons in a circular array within a cylinder block. There are two designs are most relevant, the swash plate configuration and the bent axis configuration. In both cases, the angle the swash plate or the bent axis mechanism determines the effective stroke of the piston. Bent axis pumps design. In a bent axis piston pump, the cylinder block turns with the shaft but at an offset angle. The piston rods are attached to the drive shaft flange by ball joints. Most bent axis piston pumps consist of a few basic components: port plate, spherical siding surface, drive flange, drive shaft, shaft seal, flange, retaining rings, housing, bearing, piston, axis, cylinder block. The bent axis mechanism is a pumping machine, the displacement pistons of which are arranged at an angle to the drive shaft axis. As the drive shaft rotates, the cylinder block is caused to rotate by the pistons. The pistons move up and down within the cylinder block bores. The length of stroke is dependent on the angle of the bent axis. Fluid is fed to the low pressure, then, as the pistons moves, delivered into the high pressure port. Swashplate piston pump design. Most swashplate piston pumps consist of a few basic components. Flange, shaft seal, bearing, swashplate, drive shaft, piston, cylinder block, housing, port plate. The swashplate mechanism is a displacement mechanism, the displacement pistons of which are arranged axial to the drive shaft. The reaction force of the pistons is carried by the swashplate. As the drive shaft rotates, the cylinder block is driven by means of spline. The pistons move up and down within the cylinder block bores. This movement is dependent on the angle to the swash plate. Fluid is fed to the pump via the low-pressure side, then as the pistons moves, delivered into high-pressure line.
Hi guys, welcome back to howmachineworks.com. It's Jose here. Today let's learn how an axial flow variable displacement piston pump works with the help of this animation. So please watch the entire animation and learn it. First, let's identify the components. Here this is the casing of the piston pump. That's our drive shaft, which is actually giving the drive to the pump. There we have the swash plate adjusting valves. Then we have the swash plate itself over there in green. Then comes the pistons, which actually reciprocate inside the swash plate. Okay, so that's the cylinder block in blue which rotates. So the pistons are arranged inside the cylinder block and they are free to slide over the swash plate. So what we have further, that's our outlet over there and the inlet at the top. So let's see the animation and learn further. So that's the position where the pistons are arranged. You can see when the cylinder block rotates, the pistons also rotate together with the cylinder block, sliding over the swash plate. So let's see. So that's the piston being arranged inside. The dotted mark shows how they are arranged inside the cylinder block. So that's our inlet and outlet, as I have already explained. So you can see the piston, the inside view, how the pistons are placed inside the cylinder block. So when the valve gets pressurized, the pressure is getting into the valve, result in the swash plate angle to change. So you can see when the swash plate angle changes, the piston is actually moving back. You can see that the movement of the piston back, which result in a suction. At the top the piston moves back, and at the bottom you can see the swash plate is moving towards the front. So that's the change in angle of the swash plate over there. So we have more number of pistons arranged. So you can see when more number of pistons are getting arranged, the top pistons are moving towards the back as per the swash plate angle, and the bottom pistons move towards the front due to the same angle. So I am releasing the pressure. As a result of this, the swash plate becomes vertical. So when here we have a vertical swash plate or at a 90 degree, there is no flow happening inside a axial flow variable displacement piston pump, but it becomes variable according to the swash plate angle when it increases or decreases. So how cylinder block and piston rotates, let's see that. Here you can see it's rotating over here. The cylinder block rotates, so it's a single piston that I have shown in, it's rotating, but there is no reciprocating motion for the piston over there because the swash plate is vertical over there, so there is no flow happening. And let's see the other part of it. So I'm pressurizing the valve so that the swash plate angle can be changed. You can see it's in 90 degree. When the pressure hits, the swash plate angle changes to 80 degree. You can see a decrease of 10 degree over there. So at the top, the swash plate moves back, and at the bottom, the swash plate moves towards the front. And have a look at the piston. See the arrow mark. The piston is actually moving back, and that's the reciprocating motion happening. As a result of that, a suction happens at the top. You can see at the top the suction happening over there, and at the bottom piston you can see it's actually moving towards the front because the swash plate is pushing it towards the front. So there will be getting the discharge. So as this particular cylinder block is rotating continuously, the pistons at the top end will create a suction, and the pistons at the bottom end will create a discharge. So you can see it once again. Angle increases. See the movement of the pistons at the top. The piston moves towards the back at the top, so we have a suction, and at the bottom we have a discharge. So it continues as the cylinder rotates, and when this angle increases we'll have more suction and more discharge, and when this angle decreases we have less suction and less discharge. That's why it's called a variable displacement pump. So this variable displacement depends upon the swash plate angle. So let's say it again. Suction is happening, discharge is happening, suction is happening, discharge is happening at the bottom. So that's it. So we have more number of pistons at the bottom and top. You can see how it exactly works. We have a suction at the top and we have a discharge at the bottom depending on the swash plate angle. So that's how a axial flow variable displacement piston pump exactly works. The variable displacement happens according to the difference in the swash plate angle.